Welcome to Perspectives. I'm Angie Kellen for the eBeam initiative, and I'd like you to welcome my guest today, Sergey Babin. He's the founder and president of aBeam Technologies. Hello, Sergey.
Hello.
Thank you for joining me today.
Thank you very much for the invitation.
Now, aBeam is a member of the eBeam initiative. Let's start out by maybe you explaining how and where aBeam works with eBeam Technologies.
eBeam initiative provides a very good opportunity for companies to collaborate, to exchange ideas, to attend meetings where companies from all over the world present their latest results, and you can feel the status of the industry, and you can feel also the future, where it's all going.
Now, we've been hearing some interest from the eBeam community on a hot topic that you've been discussing, the charging effect. Can you give us an overview of the charging effect problem and how it relates to some of the eBeam applications?
Electrons, they are charged particles. They charge everything they touch. When the mask is written using eBeam lithography system, the resist on the mask is being charged, and this charge deflects electrons from where they're supposed to go, so they are deflected, and this creates placement error. In a mask set, each mask is distorted in a different way, because the charging placement error depends on the pattern density and on the way it is written. As a result, the contact via may not perfectly, accurately fit on the top of the gate at the bottom, and may not be accurately fit to the metal wire on the top. And this creates chip reliability issue. Astonishing results were presented by NVIDIA and Global Foundries. They demonstrated that additional placement error of 0.1 nanometer at 20 nanometer node creates additional rate of faults in the chip of 1 order of magnitude. 1 order of magnitude due to 1/10 of nanometer additional placement. How much is actual placement on the mask? Chip makers want to see it on the level of 2 nanometers. In reality, error is often on the level of 8 or 10 nanometers, if you know where to measure. How mask shop solves this problem? They have to deliver mask in specification. So what to do about that? One typical way, mask shop writes the mask, measures CD variation, measures placement problem, and then corrects for them for these specific locations where they were measured, where they were specified. When they write the second mask looks very good in these locations again where the measurements have been specified. What about all other locations on the mask? Well, nobody cares about it, and they are not corrected. It's not mask shop problems, it's somebody else's problem. The mask is delivered with a spec, accepted, done. On the other hand, when chip makers see that rate of faulty chips is increased, they want to do something about that. So what they do, they put tighter spec on placement error to the mask shop. So mask shop is in a difficult situation. On one hand, they cannot deliver the mask in spec all over the mask. It's very difficult. On the other hand, they get a tighter spec. So they continue doing pretty much the same work. They only correct for the places that have been specified. Maybe it would be better to relax the spec for the mask, but at the same time make sure that this relaxed spec is met all over the mask.
So how is aBeam uniquely seeking to solve the challenge of the charging effect?
Well, it's a complex problem, and many companies have been working on it for a long time. IBM for a decade developed conductive resist based on polyaniline. However, this resist was not adopted by the industry, most probably because of the defect level is too high and resist sensitivity is not good enough. Another opportunity is to coat the resist with a metal layer or with conductive polymer. However, this does not solve the problem. That reduces charging but does not eliminate charging. At the same time, adds additional steps in the process and also may increase the level of defects. What aBeam is doing, aBeam predicts what will be placement error for a specific layout, for a specific mask, and then if this error map is known, then it can be corrected. So we take into account pretty much everything that is important: the mask layout, the system parameters, the writing strategy, how mask is written, resist parameters, and so on. And in this way, we can accurately predict what is the placement error map for every specific writing or specific layout. In a similar approach, NewFlare makes their charging correction. However, in that correction, instead of physical model, they use polynomial approximation of their calibration mask. And for this calibration mask, this correction will work perfectly, of course. However, there is no reason whatsoever why polynomial approximation will work for any other mask. And in this way, companies may see that for some masks, this correction works very well, but for some other masks, the placement error becomes worse. In our case, we use physical model, and this physical model, when calibrated, it delivers good results on pretty much any layout.
Recently, the eBeam initiative published a white paper on mask hotspots. Can you tell me what you think is driving the potential for mask hotspots to increase?
First of all, it's a mask complexity. OPC on the mask is now very, very aggressive. And at 20 nanometer nodes and below, very often, mask does not look the same as a desired pattern on the chip. And it makes it extremely difficult to inspect and understand where the hotspot is. And it's virtually impossible to inspect all the mask and find these hotspots and try to put additional correction to that. Much more practical and much less expensive way is to predict these hotspots and put more work on more accurate correction to increase the dose margin in these areas, and then inspect these hotspots on the mask. So this all makes it much more economical and much simpler for the fabrication.
One more question for you before I let you go. If you had a wish list, say for the eBeam initiative community to work on, what would be on that list for you?
One of the hot topics these days is multi-beam electron beam lithography. And this is a direct write and also multi-beam mask writing. And they are extremely challenging. Both of them are very challenging tasks. And this is what makes them very interesting. On the other hand, level of effort that goes into that is enormous, and complexity of problems is huge. And the same problem like charging, it's much more severe there than the problem on the regular mask making machine. And this is because in mask making you have dielectric resist, and then underneath it's a metal, while on a chip you have many dielectric layers, which makes the charge build up much faster, and which might make charging problem much more severe.
Well, Sergey, I want to thank you so much for sharing your perspectives with us today, and we hope to talk to you again very soon.
Many thanks, Angie, for having me here.
Thank you for joining us for this edition of the Fine Line Video Journal. We hope we see you next time.